Okay, so last time we finished the proof of the block theorem. So now we use the block theorem to prove theorem called Schotty theorem. Okay. Correct me if I made any mistake. Okay, so the theorem says, suppose FV is analytic in the disk D0R, so 0 of radius R, and does not assume either of the values 0 or 1. So namely 0 and 1 is not in the image, is not contained in the image set of F. Okay. Then for any theta zero less than equal to theta less than 1, there exists a constant S of F of 0 theta. So yeah, as you can see from the notation, this constant depends only on the value F at 0 and theta. Depending only on theta and F at 0 and not on the radius R or otherwise on F. Okay. So yeah, so this is only depends on theta and F0, not on the radius or on the function such that this modulus of Fz is less than this S of F at 0 theta for all Z in this closed state set at 0 of radius theta R. Okay. Okay, so let's start the proof. So assume that okay, so since this zero of radius r is simply connected, and this f is not equal to 0. Yeah, because we assume that this f does not assume value 0 or 1. So f of z not equal to 0 on yeah. So therefore, I think there's a consequence of a theorem being complex analysis that there exists a holomorphic function g such that this f is equal to e to the g. Okay. So where this g I think is up to a constant 2 pi I plus integer or something. But the thing is that here what we are using is that so there exists a holomorphic or analytic HZ on so also defined on or okay, so defined on this delta 0 radius r such that okay, so f of z is equal to e to the 2 pi I hz. So we put a factor 2 pi I up front. So okay, so because fz of this the value 1. Okay, so what fz does not assume value 1. We have this hz of this the value 0 and 1. Okay. Yes, because when hz equal to 0, we have e to the 0, which is 1, right? And then when hz equal to 1, so you get e to the 2 pi I, which you just rotate a 380 degree and then you get back to 1. So I think the thing is okay. Maybe I think it's true. Okay, so let's just forget about everything else. Okay. Okay. Therefore, okay. So yeah. So you see that since this hd also this hd obeys the value 0. So and also it's defined on holomorphic on the unit disk. So we can use the theorem that we used here to to say that there is another it's like another log function for this hz, right? So this hz is kind of like the log function for fz. So here we want to say that there's another log function for this hz, and also we want to say that because here this hz omits the value 1, so if I say the function hz minus 1, it will also omit the value 0, right? So therefore, what we can do is that we can also apply the same thing for this hz minus 1, okay? And then we'll get these two functions, okay? So that's the idea. So therefore, by the same argument, above, there exist functions we could call it phi1z and also phi2z. Oops. So okay. So here the thing is that we are letting this phi1z and phi2z not to be just the log, but it is the holomorphic square root. Okay. So so basically what you can so basically it's the holomorphic square root. Analytic. In the disk are satisfying. Okay, so how do you do that technically? So the thing is, if you let, so we know, so okay, so if you ignore this 2 pi I, okay, so we know that so there exists a function such that this hz is equal to e to the gz, right? This is by our theorem. And then, how do we construct the holomorphic square root? So basically we wanted that, okay, so you just let this, okay, so if we say that we let our function to be the function gz over 2, right? So, and then, after that, we square it. So it becomes hz again, okay. So this is our phi1, okay. All right, yeah. What happened? Okay, maybe I'm not sure what happened if the, oh. Okay, never mind. Okay. So, yeah. So, and then this hz minus 1, we set it equal to, so phi2z squared. Okay. So remember that this hz by the this hz can be chosen up to like a multiple of 2 pi, right? So and then this frequency efficiency they are also can be chosen up to like constant something. So yeah, I think it's pi I or something. Pi I, yeah. So the thing is okay. So the thing is just pick that. So they're pick any one. Yeah. So just pick any of them. Okay. So okay. So here the thing is so because okay, so here okay, so here we want to say something about this phi 1z and phi 2z. Okay, so actually they have some very special properties that we'll discuss later. Okay, so because we have some because 1 is equal to this phi 1z. So the thing is that if we subtract the right hand side from the left hand side, we will get 1, right? Yes. And then by the what's it called, like the complete square formula or something, like then it is equal to this phi 1z plus oh, sorry, I forgot the name of this formula. Remind me if you okay. The question is, okay. Whoa. Okay. All right, so we have that. Okay, so because that they constantly equal to 1. Okay, so so we have so six. Okay, yeah. So since these two when put together equal to 1, so none of these two numbers can be equal to 0, right? So so we have that. Therefore, we have this phi 1z. Maybe let's use the first one plus phi 2z. Oh, let's use the other one. Sorry, not equal to 0. Okay. So and again, so since they are not equal to 0, and then they are holomorphic, right? Okay, they are analytic. So therefore, we can use the same argument again, right? Okay. So so let's say since So their difference is equal to e to the phi z. Yeah, of course, for some phi. So let's use the notation O for holomorphic function. And then, sorry, a little bit cracked. So the holomorphic functions that's being defined on the unit analytic on the external zero is R. Okay. All right. So now. So again, okay. So then we define okay. So then we have that this phi1z plus phi2z is equal to, so because we know that, so we have the 1 over relation, right? Because we know that this phi1z times this, okay, we know that this guy times phi1z plus phi2z times phi1z minus phi2z is equal to 1. So therefore we move the other thing around, so we get this 1 over phi1z. Okay. 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 And then, which is equal to e to the negative phi z. Okay. So, okay. So you see that we get some relation about this phi1z and phi2z. Okay. So now we can use this one to. So here we write this phi1 and phi2 in terms of this phi I, right? And then plus in terms of negative phi, e to the phi, e to negative phi. So again, we can use the phi to recover the phi1 and phi2. Okay. So what we do is that, so it follows that this phi1z is equal to this, I think is, so 1/2 this e to the phi z plus, right? Because plus they cancel out, e to the negative phi z. Okay. And then, okay, so what do we have? Okay. Okay. So now we have that. Let's bring it to this h here. Okay. So here we have this 2 pi I h d, which is equal to 2 pi I phi 1 z square, which is equal to what is phi 1? Okay, so this guy squared, right? So okay, so if I square it, then this coefficient becomes 1 over 4, right? So here it becomes like pi I over 2, and then have the 6 inside squared. So for the 6 inside, you have e to the 2 phi z, right? And then times 2 copies of this one times that, which gives you 1, right? So, and then e to the negative. Right, okay. Okay, so, yeah. So we can move the 2 out, right? So we can move the 2 out. Let's see, yeah. So we move the 2 out, it becomes pi I. Okay, so let's do that. Well, and then, okay, so here we get, okay, well, so here we get this one. Okay, so we can write this f, replace this, use this to express this f, okay. So what we want is that, and we have that this, so therefore, you can write this fd is equal to, let's say f, you follow that this one, and fz is equal to e to the 2 pi I hd, which is let's see. Okay, so because you know. Okay, so yeah, so the thing is that when you take the exponential of the whole thing, right? So it is the exponential of the first part times the exponential of the second part. And when you say the exponential of the second part, it's just like this e to the I theta, where theta equal to pi, so it's equal to -1, right? Yeah, so therefore, what you get is, you get, so here, yeah, so we have -1 times e to the first part, right? So let's see, pi up over 2 times wherever the 6 is inside, right? So e to the 2 okay. All right, so maybe let's stop here. So let me see what's the time now. Okay, I think I still got time. Okay. Okay, so I'll erase the board for now. Okay. Hold on 1 second. I'll get a eraser for this one. Wait, shoot. Okay. All right, so okay, so note that okay. Oh, yeah, I raised it too early. So, yeah, so the thing is that again, as I said, this HD is being defined up to a, so I think here, so, okay, so originally, sorry, I made a mistake. So, if you have a e to the HD, right? So, then this HD is being defined up to equivalence of 2 pi, right? So basically, yeah. And then, if you define this 2 pi I, right? So then it's up to like a integer, right? So, and then, again, similarly for this phi 1 and phi 2z, right? So, I think they are also determined by this h of 0, right? So, yeah, up to like a plus or minus sign for this phi 1z and phi 2z. Wait, something bothered me. So, okay, never mind. Yeah, and also, and finally, this psi. So we look at this. So yeah, so this psi is actually also defined by this difference between phi 1z and phi 2z. After, oh, okay, so up to like an integer multiple of 2 pi I, okay. So, yeah. So, okay, so let's see. So, okay, so let's see. So since so the value h of 0 is the, let's see, is determined by this f of 0 let's say plus or up to an integer, up to an active integer, right? So so I use these arrows like up to like an integer. Okay, so this h0 is determined by this f of 0 up to integer. Okay. And then we say that this okay, so we say that this phi1 of 0 wait, hold on, I think I made a mistake somewhere. Oh, okay, never mind. Yeah. Okay, so this phi1 0. Okay, so this phi1 0 is determined by this h of 0 up to, I think, a plus and minus. plus or minus sign, right? Yeah, and then for this okay, so for this phi2 of 0, and then it's also determined by this up to plus or minus of h0. And then we have this and finally we have this psi of 0 is determined by this phi1 0 minus phi2 0 up to a 2 pi I z. Okay, up to a 2 pi z. Okay, so okay, so therefore maybe let's say therefore for all functions fz that satisfies the condition of the theorem. Okay, so yeah, so for all functions the condition of the theorem. And have a specified value at the origin. Okay, so say f at 0 is equal to alpha. For so number alpha independent okay of f. Okay, so this f could be anything, but they all this alpha is independent of this average. We may choose. I think I really need a mop or something. Okay. Okay. I'm really sorry. Okay. So we may choose the corresponding functions phi z so that they have the same value at the origin. Okay. Yeah, so again, so from the previous result, right? So we know that this hz is chosen so that this fz is equal to e to the 2 pi I hg, right? So yeah, and then yeah, it is defined up to a constant additive of z. So so then, so basically what we do is that so we want to choose this hz such that yeah, so hz is like f of 0 plus some constant, and then so h of 0 is f of 0 plus some constant, and then this h of 0, this phi1 of 0 is up to a plus or minus sign. So we say that okay, so we fix f0 equal to alpha, right? If we fix this one equal to alpha, so then we can, so basically we have the freedom to choose this hz and this wait, hold on. Okay. Okay, so basically we have the freedom to choose this hz, right? Basically, if one hz satisfies the condition, then you multiply the thing by yeah, okay. So basically, if you replace this hz by hz plus in this case, okay, result 2i. I don't think the value will change, right? Yeah, because if you take the e to the e to the infinity times e to the I, which is still giving the same thing. So yeah, so we can choose this hz such that then yeah. So okay, so this h0 is up to like yeah. So because this hz is you have this 2 pi I, right? Yeah, so it's plus integer here. So okay. So why? Okay, so here basically up, yeah. So you are allowed to choose this HD up to. Okay, so you have moved this HD, but basically by any constant number, and then that will still be a holomorphic function, right? And then it identify the result. So the thing is, if you do the same thing for the alphas, right? Okay, so you are for this phi one, you are still allowed to change this plus minus sign, and then similarly for this phi two, and then for this cosine 0. Okay, so yeah, so if this f0 is fixed, so basically, yeah, so basically we can fix like if f0 is fixed, then we can fix the fix this cosine 0 because everything else we can choose. Okay, everything else we can choose. Okay. Okay, so okay. Of course, this phi0 beta must be one of the possibilities that's consistent with this axial alpha. Okay. All right, so I'll stop here today, and then